Hi everyone, welcome to NetGate Chemistry. So in the last video of solid state we discussed about the types of unit cells. In this video we are going to discuss the first topic, which is number of atoms per unit cell present in primitive and non-primitive unit cells. So this is our next topic. So here we are going to discuss how many number of atoms in total will be present per unit cell in different types of unit cells. So first we are going to discuss about simple cubic unit cell, that is SCC. So you know what is an SCC in simple cubic unit cell. Atoms are present at all the 8 corners only. Okay, before starting this, I want to tell you about some of the basic concepts of a cube. So before starting your SCC, I would tell you about the basic terms related to the cube. A cube has, we have to find first what are the how many number of edges, how many corners, how many faces are present in a simple cube. So before starting SCC, we'll look for the edges in a simple cube. Edge is basically this side, which is represented like this. If you count the number of sides or edges, they come out to be 12. Corners are 8. 1, 2, 3, 4, 5, 6, 7, 8 corners are there, and faces are 6. That is your front face, back face 2, left face, right face 4, up and down 6. There are total 6 faces in a simple cube. Next are face diagonals. That is total number of diagonals present in the faces. So if you consider only one face, suppose this is the front face, this front face is present here, this face will be having 2 face diagonals like this, and there are total 6 faces. One face is having 2 face diagonals, so 6 faces will be having how many diagonals? 6 into 2, that is 12 face diagonals. Next is your body diagonals. Body diagonals are total 4. How body diagonals are present, you have to see. Suppose this is a point and this is a point. This is going to be one body diagonal. This and this second, this and this third, and this fourth. Basically, which is cutting the cube into halves. These are your body diagonals. So there are total 4 body diagonals in a cube. Now I want to discuss a little bit about the contribution of atoms which are present at each of these sites. So contribution per atom of a given atom present at, first is your, if atom is present at face center, how much it is going to contribute to the unit cell? It is going to contribute half. Okay, how? Suppose this is a cube and one atom is present at this face, so half of this atom will be present inside this cube and half of this atom will be shared with the adjacent cube. So only half of the part of this atom is shared with one lattice, with one unit cell. So face center contribute only half of the atom. So now second is your body center. Body center it contributes full. For example, we have seen in this case of BCC, this atom is present inside. This whole atom is inside the unit cell, so it contributes one full atom. So body center's contribution is one full atom. Third is your edge center. If atom is present at edge center, what is its contribution? Suppose this is a unit cell and atom is present at this edge. Full atom is present at this edge. So only 1/4 of the part of this atom is going to be inside this cube. Remaining will be shared by three other lattices. Three other unit lattices. So only 1/4 of this portion of the atom is shared by unit cell. So edge center contributes 1/4 because there is one sphere. Okay, so 1/4 part, this 1/4 part is shared by one unit cell. This 1/4 part is shared by the second one, this 1/4 by the third, and this 1/4 by the fourth. So this way one atom contributes, if it is present at edge center, it contributes 1/4 atom. Okay, so these are the contributions. So in order to find out the number of atoms present per unit cell, you have to use this formula, that is number of atoms present per unit cell will be equal to the contribution multiplied by the number of sites occupied. Okay, sigma. Okay, so how to use that, we'll see one by one. First case is your simple cubic lattice. In simple cubic lattice, atoms are present at all the 8 corners. So in order to find out number of atoms present per unit cell, we have to see the contribution and the number of sites occupied. The number of sites which are occupied are 8. 1, 2, 3, 4, 5, 6, 7 and 8, and the contribution will be, it is present at the corner. So how much contribution does corner gives? It is 1/8. Corner gives 1/8 contribution because this corner atom will be shared by 8 unit cells. How? One unit cell will be present adjacent to it. Okay, one will be behind and one will be adjacent to the see, one atom is here, one unit cell is here, other is adjacent to it. Okay, next will be behind this, and fourth will be here behind this unit cell. 4 and 4 will be above this, 1, 2, 3 and 4. So if an atom is present at this corner, it will be shared by 8 unit cell, like 1, 2, 3, 4 and 4 above, 1, 2, 3, 4, total 8. So one atom at the corner contributes 1/8 to one unit cell. So total number of atoms per unit cell will be 1. For FCC, yani face centered cubic unit cell, atoms will be present at 8 corners as well as the face centers: left face, right face, front, back, up, down. This will be your FCC. So we'll see contribution and number of sites occupied. So first of all, we'll see contribution by the corner atoms. There are 8 corner atoms and contribution is 1/8 each, plus, because we have used sigma here, that's why plus. Now atoms at face center, there are total 6 atoms at the face center. Each face center is contributing half, which we have already discussed. If you solve this, 3 plus 1, 4. There are 4 number of atoms per unit cell in FCC. Next, third case, BCC. In BCC, atoms are present at all the 8 corners as well as the body center. So first of all, we'll take the number of atoms per unit cell present according to the corners. So there are 8 corners, each corner contributing 1 by 8 plus 1 at the body center, which contributes 1 full atom. So it comes out to be 1 plus 1, 2 atoms. Fourth is your edge CC. Now what is edge CC? See, in edge CC also 8 atoms will be present at the corners, and atoms will be present at the center of each edge also. So there are 12 edges, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so at 12 centers of each edge there will be an atom present. So first, for the corners, there are 8 corners and each contributing 1 by 8, and there are total 12 edges at which at the center atoms are present, and each atom present at the edge contributes 1 by 4. So if you solve, it comes out to be 4. Next is your end CC. In end CC, atoms are present at 8 corners as well as 2 opposite faces, any of the 2 opposite faces. Suppose I'm taking this up face, so one will be present here and one will be opposite to this, that is downward face, this way. Other possibilities can be left face and the right face, and the other could be front and the back face. So there are total 3 possibilities. So if we take this case, there are 8 atoms, each contributing 1 by 8, which are present at the corners, plus if atom is present at this face center, it is contributing 1 by 2, and there are 2 atoms present at the face center, so it comes out to be 2. Okay, so these are the contributions. Here is one more, that is diamond cubic crystal. Here atoms are present at corners plus face centers plus half of tetrahedral voids which are adjacent. So before discussing this, we need to have some knowledge about the voids. So voids are basically present in your FCC structures. So I think that is going to be enough for this video. In the next video, we are going to discuss about the voids and then FCC and relation between radius and the edge length. So that's it for this video. Thank you so much for watching.